Today, we're diving into the invisible world that's all around us. We're talking about gases and the one single elegant equation that lets us crack the code of their behavior. I mean, think about it for a second. This was the huge puzzle facing early scientists. Gases are everywhere, right? But they're slippery. How in the world do you even start to make rules for something that seems totally random and chaotic? And in the real world, it is chaotic. You've got zillions of tiny particles just zipping around, crashing into each other, bouncing off the walls of whatever container they're in. Plus, they have these things called intermolecular forces, tiny little pushes and pulls between them. And all those little details make it almost impossible to perfectly predict what a real gas is going to do. So to make any progress, scientists had to get clever. They had to simplify the problem. And they did that by dreaming up the ideal gas. Now, you can't find this stuff anywhere. It doesn't actually exist. It's a hypothetical model, kind of a scientific thought experiment. The whole point was to ignore all those messy, complicated bits so they could get to the core of how gases actually work. So this whole idea rests on two big and kind of bold assumptions. First, we pretend that the gas particles don't interact at all. No pulling, no pushing, they just fly right past each other. Second, we pretend the particles themselves are so tiny they take up zero space. They're just dimensionless points. Now, obviously, that's not totally true in reality, but making these simplifications lets us build a model that works amazingly well under most normal conditions. All right, so with these new, simpler rules of the game, scientists could finally start looking for patterns. It was like they were detectives, uncovering individual clues, simple laws that connected one property of a gas, like its pressure, to another, like its volume. The first clue came from Robert Boyle. He figured out this really neat relationship between pressure and volume. Basically, what Boyle's law says is if you take a certain amount of gas and keep its temperature the same, its volume and pressure are inversely related. In other words, if you squeeze it, increase the pressure, its volume goes down. Just think about a balloon. The harder you squeeze it with your hands, the smaller it gets. Simple as that. Next up, we have Jacques Charles, who found the connection between temperature and volume. Charles's law is a direct relationship. If you keep the pressure steady and you heat a gas up, its volume gets bigger. This is literally the principle that makes a hot air balloon work. You heat the air inside, it expands, becomes less dense than the cooler air outside, and poof, the balloon starts to rise. And the last major clue came from Amedeo Avogadro. And honestly, this one is probably the most intuitive of them all. Avogadro's law just says that if you keep the temperature and pressure the same, the more gas you add to a container, the bigger its volume will be. It's just common sense, right? You blow more air into a balloon, the balloon gets bigger. So, now we have all the clues. Let's see what happens when we put them together. Okay, so we've got our three clues. Each one is a simple relationship, a single piece of a much larger code. Now for the fun part. It's time to assemble these puzzle pieces into one powerful tool. So, from Boyle, we know volume goes down when pressure goes up. It's inversely proportional. And from Charles, we know volume goes up when temperature goes up. A direct relationship. And finally, Avogadro told us that volume goes up when you add more gas. That's N, the number of moles. Another direct relationship. And when you combine all three of those simple ideas into one, you get this beautiful, elegant equation, PV equals nRT. This is the ideal gas law. It's the master key that connects all four of those properties: pressure, volume, amount, and temperature, all together. Now, having the master key is one thing, but you gotta know how to use it, right? To really unlock its power, you have to speak its language. And that means you have to be really, really careful with the units. So, here are our variables. You've got P for pressure, V for volume, N for the amount of gas in moles. But, and this is a big but, look at temperature, T. For this whole thing to work, your temperature must be in Kelvin, not Celsius, not Fahrenheit, Kelvin only. The entire thing falls apart if you don't use Kelvin, because it's an absolute scale where 0 means zero energy. It's non-negotiable. And that brings us to R, the ideal gas constant. You can think of R as a kind of universal translator. It's the magic number that makes all the units play nice together. See how its value changes? That's because it has to match whatever units you're using for pressure and volume. The trick is just to pick the version of R that matches the units you're given in the problem. Okay, enough talk. Let's put this into action and actually solve something. We've got a bit of neon gas. We know its pressure. We know its temperature. The question is, how much space does it take up? What's its volume? So here's how we tackle it, step by step. First, and this is always the first step, you have to get all your numbers into the right units. That means converting the pressure to atmospheres, the grams of neon to moles, and critically, that Celsius temperature into Kelvin. Then you just do a little algebra to rearrange the equation to solve for what you want, which in this case is volume. After that, it's just a matter of plugging in all your converted numbers and letting your calculator do the work. And when you run all those numbers, you get 19 liters. And that's the power of this law. We just took an invisible substance and calculated a concrete, predictable answer for how much space it fills. How cool is that? So this kind of brings us full circle, doesn't it? We know this whole law is built on a perfect gas that doesn't even exist. So why is it one of the most important equations in all of chemistry and physics? Why is it so useful? Well, here's the secret. Under most normal conditions, like right here on Earth, real gases behave almost perfectly. They're incredibly close to ideal. This quote here gives us a way to actually measure how ideal a gas is behaving. If you rearrange the formula and solve for PV divided by nRT, a truly perfect gas will always give you an answer of exactly 1. A real gas might be 0.99 or maybe 1.01. That tiny little deviation from the number 1 tells you exactly how much the real-world messiness is starting to matter.
So yeah, the model is a simplification. It's not perfect, but it doesn't need to be. It's an incredibly powerful tool that gives us a baseline, a fundamental understanding that gets us remarkably close to the right answer every single time. It lets us make sense of that chaotic, invisible world of gases.
And that leaves us with one last thing to think about. To understand a really complex, imperfect system, we started by creating a perfect, simplified model. And this approach, it's used everywhere. Not just in science, but in economics, in engineering, maybe even in how we think about our own lives. So the question I'll leave you with is, where else do you see us using these ideal models to get a handle on our complex world?